In this video, we're going to discuss Chern insulator, P-wave superconductors, and chiral spin liquids. The idea will be to use a honeycomb lattice, and on the vertices of the honeycomb, we will put fermions, Majorana fermions, or spins. And they will lead to this interesting state of matter. So you already heard about the honeycomb lattice. So let's see how we build the honeycomb lattice. We first have these two chains of crimson and gold atoms. We move them in this fashion. Now the emphasis in this in this video will be on the fact that the Z bond may be, we call it Z, may be different from the Y bond and the X bond. This, we will put emphasis on that situation. So as you know, the unit cell of the honeycomb lattice is a rhombus, a diamond, contain two atoms, the crimson and the gold atoms. So what we put emphasis is on, and you can describe it in terms of three vectors, delta 1, delta 2, and delta 3. And as I said, what we want to do is to discuss graphene-like Hamiltonian within equivalent bonds. So we will have the X bond, the Y bond, and the Z bond. The Hamiltonian in this situation, written in terms of this vector, CKA describe the crimson, CKB describe the gold atom, and HK will be, the Hamiltonian will be written in this form, which H12K is equal to Tx e to the ik delta 1 plus Ty e to the ik delta 2 plus Tz e to the ik delta 3. And as I said, in this video, we pay attention to the situation when Tz, Ty, and Tx may be different. So the energy is given by plus minus the absolute value of H12K, and here we take Tx, Ty, and Tz to be real numbers. So as you heard already in Shahal description and Raquel description of graphene, near the two K and K prime point, we will have these Dirac cones that describe the motion of describe the energy of the system. We can think about in the AB space on vectors that wind around this Dirac point, clockwise or anti-clockwise. Formally, we can write at the vicinity of this Dirac cones, the Hamiltonian is plus minus V Fermi, Kx plus IKY, Kx minus IKY. Or in terms of matrices, sigma X and sigma Y, in the AB space, in the crimson gold space, it will look like that. Importantly, we will not have this sigma Z term. So sigma Z term is excluded from this Hamiltonian. So let's look at it more carefully. This is in K space, looking from above about a few Brillouin zones. This is Kx, Ky, and near the point K prime, the system wind anti-clockwise, and near this crimson point, it will wind clockwise. Now what happens, so that configuration is for Tx equal to Ty equal to Tz. What happens when Tz is larger than Tx and Ty? So then, following, analyzing this H12K, one can easily convince himself that that's what happened, that these two vortices approach each other when Tz is larger than Tx, which is equal to Ty. This is what you will get from analysis of this H12K. Eventually, when we increase Tz to be twice large than Tx and Ty, these two vortices meet each other and annihilate each other. So you can think about it as a topological phase transition between a situation in which we have two vortices with zero, which Dirac cones that touch each other, and then they annihilate each other, and a gap is open in the system. So I prepared for you a short video that just described that. So what we see here, I'm looking at the situation when Tx plus Ty plus Tz is equal to 1, so that the bandwidth remained constant from -1 to 1, and we change Tz while fixing Ty equal to Tx. So we start a situation where all Tz is equal to Tx equal to Ty, and you see here the two Dirac cones. So let's see what happened when we increase Tz, keeping this normalization relation. As we change Tz, you see how the two Dirac cones approach each other. Again, Let's see how the two Dirac cones approach each other until they annihilate each other. This happens exactly at Tz equal to 1/2. So we are in a situation when Tx equal to Ty equal to 1/4 and Tz equal to 1/2. As we continue to increase Tz, then a gap is opened in the system and there are no Dirac cones. So this is a situation in which we have a graphene with inequivalent bonds. So as I told you, we focused on a subset of parameters, namely Tx plus Ty plus Tz equal to 1. So you can convince yourself that form in this three-dimensional plot a triangle of that point. For example, when both Tz and Ty are equal to 0, Tx must be equal to 1. Now, if I look at that triangle from that side, it will look in that fashion. So let's analyze what the result that we obtained. So these lines are Tz equal to 2Tx equal to Tty equal to 1/2, and there are additional two equivalent lines. What we found is that there are two phases. The A phase is gap full. There is a gap in the system. And the B phase is a gapless state. This describes the Dirac cones of graphene. Now, as you heard already from Shachal's talk, when we add next nearest neighbors, we will get the so-called Haldane Chern insulator. So here we introduce this second nearest neighbor tunneling. And the important thing is that these Hoping matrix elements are now complex number with the proper phase that they accumulate in these paths. Now, the important thing is to keep the total magnetic field in one unit cell equal to 0. So a nice thing to see that is to concentrate on this diamond and put positive flux around the crimson bond and negative flux around the gold bond. The total flux through this unit cell is 0. So as you heard already in the previous videos, with next nearest neighbors tunneling, the B phase become gap full, and we get a Chern insulator with Chern number equal to 1. On the edge of the sample, so what happened now is that the system in the bulk is gap full, and there is an edge state, a chiral fermion in this case. So this is the Chern insulator case. Now, what we want is to describe P-wave superconductivity in that manner. So how we do that? We're going to substitute each of the fermions that gave us this Chern insulator. We're going to substitute them by Majorana fermions. So we'll have this star representing a Majorana fermion, and I'm going to substitute all the positions of the honeycomb vertices by Majorana zero modes. And these Majorana zero modes are coupled. So we can almost guess immediately what will be the results of this honeycomb structure. So again, we will have the same set of phases, a gap full phase and a gapless phase. The A phase will be the so-called trivial P-wave superconductors. There will be no edge mode, nothing of that type. The B phase will, without next nearest neighbor tunneling, the B phase, we will have a gapless P-wave superconductor with a Majorana cone, which will give us the gapless excitation. Now, when we add next nearest neighbor interaction, then things become more interesting. The coupling between neighboring Majoranas always have an I, right? Because these are two Majorana modes. They are real number. It has to be a term in the Hamiltonian which is Hermitian. So the complex conjugation of I gamma 1 gamma 2 is minus I gamma 2 gamma 1. I exchange their position. I will get an Hermitian Hamiltonian. So each next nearest neighbor's bond will have a plus I or a minus I. And so as we make a triangle of that type, we must collect an I or a minus I, depends on the sign of the bonds, along this path. This will lead eventually, with next nearest neighbor interaction, to a gap full phase, which is a P-wave superconductor, and a state on the end, which is a chiral Majorana mode on the edge, a propagating state. We met this state already in the wire construction of a P-wave superconductor. So that's what we expect to see. This will not be a full fermion, but rather half of a fermion, a Majorana mode that propagate on the boundary. So this is the P-wave superconductor, which we get by substituting each fermion by Majorana fermion on the honeycomb lattice. Now let's continue. What is interesting, and I would like to emphasize in this state, that by gate, for example, by applying, let's imagine that this is one of the wires that we discussed before in the course. So with a gate potential, I can tune the coupling between these two Majoranas. I can make it from being positive to being negative. And then in each loop that cross this line, the number of bonds will not be positive. So if all of them are plus, then it's plus time plus time plus time plus time plus. It's on the loop, I have a positive number, and here in this situation, if I multiply the bonds on the loop, they will be negative. And that actually one can convince yourself that that introduced a vortex in the system. So what we saw in the previous videos that I described, when we change the boundary condition on the loop, we'll have a vortex in the system, and that will contain a Majorana zero mode. But that is we have to introduce it by hand here. It is a gate potential that change the coupling between the two Majoranas. In the case of spin system, it will be different. So here it's external change in the properties of the system by an external gate potential. Now what I would like to discuss is how to continue and make the system a bit more complex to put spins on these vertices of the honeycomb. So to do so, I'm doing it in a very special way. Let me first decorate each Majorana by 3 satellite Majoranas in that fashion, both for all these Majorana modes in that fashion. And now, also for the gold one. And now I want to couple these two Majoranas. So when they are coupled, they are gapped. They will not change the spectrum of the system. So I didn't do anything so far by adding these, by decorating the system with additional Majorana modes. These are gapped system. I still have a P-wave superconductor with edge modes, if I have next nearest neighbors, and so on. And now start the fun of the situation. What happened if I put these triangles and I fix the charge in these triangles? That would be done by, for example, by adding into the system Coulomb interaction forces on these islands. So if we fix the charge in this triangle, then with another charging energy EC, so what we saw so far that for T much larger than EC, for example, when EC is 0, then we have a P-wave superconductor. And what I would like to discuss now is what happens when T is much smaller than EC. Then, due to this large charging energy, we expect the system to be insulating. But it will be a very special insulator with very interesting properties. So let's see what happens when EC is much larger than T. So in order to analyze that, I put here 4 Majoranas, which I call them C, BZ, BX, and BY for obvious reason. This was the Z bond, this was the Y bond, that was the X bond. And I define 2 fermions, F1, which is C plus IBZ, F2, which is 1/2 BX plus IBY. And let's analyze a bit the mathematics of these modes. So when I have large charging energy, I fix the charge on this island. So that means that F1 plus F2, which is the total number of fermions on the island, is fixed. And I choose it to be fixed to be 1. Just fix, that's what is important. So let's see what happened with this fixing. I just calculate these operators, substitute for F1 what we wrote before as C plus IBZ, and for F2 as BX plus IBY. Then I open these brackets. We'll have C squared plus BX squared plus BY squared plus BZ squared minus 2I BZC minus 2I BX BY. And remember, the C squared is equal to 1, BX squared is equal to 1, and so on. So these 4 will be cancelled by that one. And what we get is that BX I can also divide by minus 2I, so BZC plus BX BY is equal to 0. I multiply that by BX BY. So I will exchange the position of bx and by here, and use again the fact that bx squared is equal to 1, by squared is equal to 1, and I get this result, that bx times by times bz times c has to be equal to 1. So when I fix the charge, I get this constraint in the system. And the nice thing is that with this constraint, I get for free spin algebra. So let's see how that happens. If I define Sx to be equal to IC Bx, Sy to be IC By, Sz to be IC Bz, then these operators will obey the spin algebra. So I just multiply Sx times Sy, and the important thing in this stage is I multiply by Bz squared, which is 1, C squared, which is 1, and now I can exchange the position of 1 Bz and C here. Using the constraint, we got this minus Bzc, and then using the definition of Sz, we get this Isc. So this is by introducing this charging energy, we had this constraint, and we get this spin algebra. So now, with this situation, I can now think about what these tunneling processes, what they bring into the story. So now I cannot change. If a fermion tunneling from here to here, I will break this constraint. I change the number of particles in these boxes. So the only interesting possibility is that a fermion will tunnel from C to C along the Z bond and come back through the B's. So that will lead to the following type of expression, minus TZC. TZC is the strength of tunneling along the C bond. TZB is the strength of tunneling along the B bond. And we do a second order perturbation theory, and we get this type of operators. So in these models with charging energy, in addition to the CC coupling, we will have BZ coupling. So, and these are known, and these terms, these BZ do not commute with the charging, with the constraint, but they do commute with all the other terms in the Hamiltonians. And these are known as the Z2 gauge field fluctuations. So again, using our definitions of, I can rearrange this term in the following fashion, and using our definitions of spin in terms of the Majorana operator, we'll get a term which looks like JZ, SZ, SZ. So that we can think about spins which sit on, instead of these 4 Majoranas, on each vertex. So we got a honeycomb model with spins sitting on the vertices. And this is known as the Kitaev honeycomb model. The nice thing is that Kitaev starts from the spin models and use these Majoranas as vehicle to understand how the system behave. Here we do the opposite. We start from Majoranas, we introduce the charging energy, and in the limit of very large charging energy, we got this spin model. Now this is very different from the P-wave superconductor. For example, we know that if we do a gauge transformation, we substitute each the C in this gold state, we substitute C by minus C, this will change the value of the interactions in each point. And we gauge fluctuations all the time. These B fields that sit here can be plus or minus. They can fluctuate as long as they keep no loops in the system. So the ground state of the system will be formed by all gauge field loops with 0 fluxes. Now, unlike the P-wave superconductor, when we introduce one flip in the system, when one of the B's flips, then we will have two vortices excitations in the system, but this is unlike the P-wave superconductor. When you had to introduce it by external gate, this will be an internal excitation in the system. So these two vortices are internal excitations of the system. So let's summarize the honeycomb model. We'll have the A phase will be an insulator phase. This is known to be I didn't show it in this video, but this is known to be the toric code due to the Z2 gauge fluctuations. Ehresberg will discuss that model more. Without next nearest neighbor tunneling, we get a B phase, which is gapless spin liquid. And when we include next nearest neighbor tunneling, we get a gap-full chiral spin liquid with an edge mode, which is very much like a Majorana mode. It is interesting to follow how we study this problem. We study two limits. One in which we didn't have any charging energy in this triangles. This will be that side of the problem, EC equal to 0. That was the chiral P-wave superconductor due to the coupling between the Majorana zero modes. In the limit of very large charging energy, we map the problem onto the Kitaev spin model. So the system is described by a chiral spin liquid when we have next nearest neighbor interaction. The transition between them is an interesting, how the transition between them occurs, it's an interesting question which I leave for you to study. This is a very interesting problem. To summarize the whole video, we study a honeycomb model with different objects on the vertices. In the Haldane case, these were fermions. In the P-wave superconductor, these were Majorana zero modes. And in the Kitaev case, these were spins. The charge is conserved in the case of Haldane. These are simply fermions. Of course, the charge is conserved. In the P-wave superconductor, we have a term side dagger in the problem, so that the charge is not conserved. While in the Kitaev spins case, of course, these are neutral mode. The charge is conserved. We described three different phases. The first phase was when one of the couplings, Jx, Jy, or Jz, was larger than the other two. Or in case of Haldane, Tz is larger than Tx and Ty, for example. This is the gapped phase. In the case of Haldane, this will be the trivial insulator, which is an insulator both in the bulk and there is nothing on the edge. In the case of a P-wave superconductor, it is a trivial P-wave superconductor. There is a gap in the system. It's still a superconductor, but there are no edge mode. In case of Kitaev, we get the toric code, which is due to the Z2 gauge field fluctuations. When the couplings are more or less equal to each other, we get a different phase. This is a gapless phase, which we call phase B. In the case of Haldane, this is simply correspond to graphene, a Dirac cone, which is very similar to the graphene case. When they are exactly equal, this is the graphene case. In the P-wave superconductor, we will get a very interesting superconductor, which is a gapless superconductor with a cone of Majoranas. In the case of Kitaev, we will get a spin liquid phase, which is gapless in the bulk. Now, when we include next nearest neighbor interaction, in the case of Haldane, we will get the chiral Chern insulator with a fermion edge mode on the edge of the sample. In the case of a P-wave superconductor, when we include this next nearest neighbor interaction, we get the so-called chiral P-wave superconductor, where there is a gap in the bulk, and on the edge, we will have a Majorana mode propagating in a certain direction. In the Kitaev case, the bulk is gapped, and there is a chiral spin neutral mode of spins which propagating on the edge. So this was a summary of the first part of the video. Let's now move to the second video.